Hello. Sometimes you get people who come and ask, I'd really like to understand about FPAs and where they're going. You're like, great, let's actually have a short conversation. A good overview is sort of this Proceedings IEEE paper in 2020, so there's kind of a good overview to about that year. And what you mean by when you look at an FPGA, it's a field programmable gate array, which is basically routing and logic with IOs. And an FPA is basically going to be logic, routing, IOs, as well as analog components. So the FPA is sort of your mixed signal equivalent of an FPGA. And there's a lot of interesting questions of what is the granularity in terms of the various blocks and aspects that you may be seeing in the system. You could end up imagining having in your various cabs have different larger blocks, or they could be levels of transistors, and we could get different things. But we'd really want to get fine-grained capability with really with less than coarse-grained cost, if at all possible. And in so doing, that's actually turned out to be an incredible aspect with the structures which we now call the system-on-chip FPAs, which have all of these aspects have been used for classifiers and both machine learning, inference, been used. There's a whole tool infrastructure, there's a whole infrastructure for building and using these devices. And what helps is the fact that the computation actually can be done in the routing aspects. So the crossbars that you actually get in routing can give you things like vector matrix multiplication, rather than needing to have separate elements and blocks that you see in FPGAs. And the net effect of that is that this sort of computing in memory concept really is because I can compute in the switch elements because I can use a single device. Really, really cool concepts all the way through. So with that, you can kind of see, this is a really neat and interesting technology that we can see today. That being said, sometimes you still get the questions. Well, what could these FPA devices become? Say, starting from this 2020 perspective. And, second, how will these FPAs reach their potential? And, or how are they going to get there? And the second one is probably a little more detailed question, but let's actually kind of focus on the first question and see how far we can go with that. And to do so, I think it just requires a little bit of a journey. So let's kind of take a nice little walk, kind of walk down the path and see where things might lead us. Well, there was a day when the FPAs came and they were just adorable, when they just sort of came out. And when they did, we kind of made sure that we actually gave them plenty of nutrients. We fortified them with floating gate elements, which enabled the programmability. And lots of people said, that'd be great, but it looks like just a nice little toy. Well, she grew up, and then she starts walking along, and we start seeing some slightly bigger chips. And people think, okay, maybe it's good enough for prototyping, but there's some other questions. Then what you get is a little bit bigger, a little bit more capability. They start to grow up, and you start actually seeing a whole range of functions, to which then people say, well, yeah, could you build a real system out of it? What's the whole larger structure there? And she just keeps growing a little bit further, and eventually you get like a whole system chip like the SoC FPA structure. And then people say, well, you got any tools? And you're like, yep, got those too. And now this creates a whole conversation of what's possible. But then you ask the question, well, what is she going to be when she grows up? And like any child, it's hard to tell, right? Because, she might end up getting larger and then being, in a boardroom, maybe running the boardroom, but, maybe even have higher ambitions, and we could see where that would go. So to figure this out, this is going to require sort of a closer look. So this is kind of where we want to kind of dig into this. Now to do that, I want to first take a comparison between the core logic blocks, one of which is a CLB, computational logic block, which is basically a LUT and an SRAM. In that case, I have one CLB being roughly about 8 lookup tables, and that's what a LUT would stand for. And that's basically, you get nice simple state machines out of this, which is really quite a lot of computational complexity in one spot. Well, a cab is going to then be the floating gate routing and floating gate circuits. And you say, well, what's possible there? Well, in one cab, you could easily imagine having a full small auditory classifier. You think, okay, that's kind of significant, where you actually have like a vector matrix multiplication and winner-take-all block, probably also with some of the earlier subband signal processing elements in the element. And there's quite a difference between a simple state machine and like a full classification structure all in one cab. It shows the power of the analog floating gate programming, both in the circuit elements, but also within the routing and how you can use it, which also leads immediately to the fine-grained routing and computation, things like having the vector matrix multiplication in the routing. And so you see the huge computational improvement that you would typically expect by the by looking at sort of analog techniques versus digital techniques and the classical sort of energy efficiency that's been predicted. So you say, this is great. And you start to say, well, how big could she end up growing? Well, as you start to look at the process nodes, we could start to say chips now in our classical 350 nanometer process, but the number of cabs will then likely keep increasing. And this is actually based on some actual data. You expect this is kind of going to be roughly, quadratically with, 1 over the node value. And you can actually see this in terms of some very careful discussions and also data in terms of what these structures would look like. Okay. Well, if you do that, then what happens is you can see a whole range of devices and gate structures. And again, there's always this question in FPGAs of the equivalent number of gates. You can imagine at sort of this 14 nanometer node, you're at 100 to a million gate level-ish. The largest FPGA state are 20 million gates. Again, very kind of sort of unclear number, and there's a lot of things that could be asked, but let's kind of just start to get kind of a comparison. You could imagine this directly fits, and also as a sort of almost a direct replacement when you start getting the 40 nanometer to 14 nanometer for FPGA devices. But what gets interesting is then you say, well, what about all the vector matrix multiplication elements? And remember, this can be done right in routing. Now, how much is roughly a reasonable number? Well, typically we're going to look at maybe about 1/8 of the fabric switches to make a VMM, because you're going to have a few other things. So that's kind of a good conservative number to work with. But what you notice is going from today's kind of numbers, which are in the 100,000 range, that you can go all the way, once you get to 40 nanometer, you're in the millions, to the hundreds of millions of devices. Well, if you actually look at some basic concepts, vector matrix multiplication, our weights, you look at sort of the largest neural networks built today, they're on the 100 million weight kind of levels. And you think, well, wait a minute, that usually gets run on a supercomputing system of some sort, where you start talking about getting like, a petaMAC per second in this kind of device. Or we might imagine being able to do this on 2 chips, including doing the on-chip training through this system. Well, that's pretty incredible, because 2 chips then fits into like a typical smartphone. Wow, okay. Now that gets interesting, but that only begins to get part of the story, because now you say, what's the total number of VMM computations per second? This has a lot to do with knowing how the bandwidth scales in the FPA, so that continues to scale on top of the density. And what you see is that you get to like a 32 or 40 nanometer structure, you're talking about the number of MACs and the operating frequency. Okay, this is getting kind of cool. What you find when you start getting to numbers around a petaMAC or so, again, it's like that big supercomputing system. 10 to 20 petaMACs maybe in a really, really maybe cutting edge system in some places. But you could imagine doing this on a single chip in 32 nanometer. And what you might imagine is something like almost an analog GPU kind of element, where you've got a whole range of like analog processors maybe in some sort of dense array. And immediately when you start to think about that, there's a number of applications, but this is, again, could be a single chip module. When we start having a couple of those together, you could imagine this being really important for image processing, where you actually have little regions cover each of sort of the small regions of an image. And there's incredible things that are possible. And you can imagine, 10 teraMAC kind of computations, sort of 10 to 100 milliwatts of power. I mean, just running this through sort of standard imagers. And the capability is rather amazing. But you could also then take this and imagine a common module for an RF system, where you basically just take antennas going through TR switches maybe outside of it, and then a whole bunch of stuff all inside the chip, all the way through the computation. And you might say, well, that might also fit in this sort of range, trying to a couple in the petaMAC range, again on a single chip, maybe less than a petaMAC. But it's incredible what could be done even in that sort of block, and you could imagine how you could field that. Here's the cool part. Again, this sort of server is going to be in around the 10 megawatt kind of ranges. In this case, we're going to be talking about something, in a very different place, because 10 megawatts is going to require things like hydroelectric dams. In this case, we're talking 6 watts, which could even still be done with a large battery. But even one step further. So imagine we're taking a device that's running at 1 milliwatt, and you try to think, okay, well, let's say a 45 nanometer node, that's, at 1 teraMAC per second, you're at sort of your clusters and sort of small clusters of GPUs. That's a huge amount of computational possibility, as we've already even given a couple demonstrations of it. But this could run on a simple battery device. Take a simple battery and at that level, this would run at like 2.5 months. What's even cooler is then you imagine at like 1 microwatt, and then you say, well, okay, again, 40 nanometer-ish process, you're talking about 1 gigamac, which is maybe the level of a very high-end laptop. But in theory, the power is so low that I could get away with this with almost no battery at all. That's a discussion talking about energy harvesting, where you talk about around 10 microwatts per centimeter squared, which is a pretty typical number for all sorts of structures, with the one exception that if you happen to be doing solar in the desert, like say in the Phoenix Desert where you can see the saguaros, which I just so close to my heart, this is the kind of thing that you would see. And so this is pretty incredible, but even one step further is, at 100 centimeters, I'm actually back up to the 1 milliwatt spot and still not needing any battery power. Well, 100 centimeters is basically the area that you might see of a cell phone. And so now you start to think about what's possible in all of these ranges. And that's just the conventional computing measures, the things that we typically are used to thinking in sort of a digital standpoint in terms of multiply accumulates. But realize that FPAs can actually compute over continuous time, continuous values. And so you're computing over reals instead of integers. Somebody's going to come by and say, yeah, and why does that matter? It's just, that sounds like a nice math thing. Well, it's a completely different computational complexity. And you can get into great depth here of asking the question of, well, what's the difference of computing with real values and real value Turing machine structure and digital Turing machine structure? Digital Turing machine structure is basically what you see that runs every single laptop in digital computing, whereas the physical real stuff computing is what you'd see for any of these analog structures, FPA structures, and so forth. And so, again, laptop makes a really good version of it, but the FPAs have even more options. And what makes this work is that on the analog side is that there's a whole framework of numerical analysis, architecture, and abstraction that's coming up, which is kind of necessary, much like the digital side. So all this seems very, very reasonable. And then there might be the question, well, so are you saying that like NP problems could be optimally solved in polynomial time on an FPA? Maybe. You're saying that FPAs could do quantum computing expected applications? Almost certainly. Okay, hold on. I gotta answer this question then. So you're saying that doing that, I could potentially take my cell phone. I might be able to one day have NP problems solved, polynomial time, and be able to solve these things for this huge quantum computing infrastructure all on the same device. Yeah, pretty much. That's a possibility. So when you begin to look at the FPAs, and it's just such a beautiful thing, and when these little, when the structures, they start off so small, and we just try to nurture them and work with them from, over the last 20 years. And so you begin to see the small ones, which are small FPA ones. Eventually they start, crawling. Then they start actually getting to be bigger and starting to touch on system level design, become full systems. And then we can imagine where she might go, and just all of the other possibilities that could happen. We've seen so much over 20 years, you could imagine what could happen over the next 10 to 20 years. And you just begin to imagine, the places you'll go, the places you'll see.